Hello, welcome to New Racing Tutorials. My name is Lloyd James and today we'll go over the more advanced setup aspects of running a full car simulation. These include the rotating wheel and moving floor boundary layers, as well as the use of monitor points in complex simulations. We'll start with the moving floor. This requires a new boundary that we will very engineeringly name moving floor. This is a wall that is the location of the predetermined floor selected in the meshing. We add a wall velocity of the equivalent speed in the correct direction. Due to the setup of the simulation, a negative x direction is required, while there is no movement in the y or z directions, as we are assuming the car is moving in a straight line. We'll now begin creation of the boundaries that represent the rotating wheels. These require a coordinate system to rotate around. Create the coordinate system's name to match that of the name selection created in the meshing step. This reduces confusion when selecting the geometry locations. Now there is a coordinate system, a new boundary must be created to activate the rotation of the wheel. It will be named the same as the coordinate system to prevent confusion, as a wall that has a location matching the name. There's a no-slip wall with wall velocity, however this time we will use rotating wheel. The angular velocity for this size wheel is 71.73 radians a second. To check the direction of rotation, we use the right-hand rule with our fingers curling in the direction we like the rotation. Since our thumb is pointing opposite to that of the coordinate system, this angular velocity must be negative. We now change our rotation axis to that of the new coordinate system and the wheel is now set to rotate. This process is repeated 3 more times. Now it's time for some digitally induced answers to our state. While that happens, I'm here to talk to you about why that's necessary in a whole car package simulation. Although not present on this car, wings will be present on future simulations done in ANSYS. These wings are very sensitive to changes in the air around them, and stationary and rotating wheels give different wake paths and take-up paths of air as they pass through it. Given the team's current desire to improve simulations of the overall package, it is critical that rotating wheels are added into this new simulation style. Now this is complete, we'll quickly discuss monitor points. The reason monitor points are used in a simulation like this is that due to the nature of mesh independence studies, there can often be meshing or geometry errors that create effects that are not desirable. These can sometimes not be picked up by ANSYS's monitoring of the momentum equations. Therefore, it is good practice to have one of the monitor points on a wheel for force and on a wheel for y+, as well as another monitor point somewhere else for force and another location for y+. This enables you to observe wild changes in forces generated by singularity points that ANSYS might not be picking up. Once monitor points have been applied, the setup is complete and the simulation is ready to begin. To begin a simulation, open the solution dialog box. Since this simulation is destined for mesh independence, it's recommended to enable double precision, as this will reduce the chance of errors once the elements get very small near the wall. Local parallel computing is also recommended, otherwise the sim time will blow out to weeks or months. The number of cores your computer has can be found by going to the Performance tab of the Task Manager, which can be accessed through Control-Shift-Escape. The number of logical processes is the one that we're interested in, and we want to take this number and enter it -2 into the partitions box to enable the computer to function normally, and in some cases increase the speed of the run rather than having all CPU cores running at the same time. With this, the run is ready to be started.